In this video, we're going to take a look at some practical problem solving using our central limit theorem, and we'll look at an example. So the practical problem solving, the first thing that we need to do is we need to check to see if we have the requirements, right? So is the sample size greater than 30? If that's there, then we're fine. Is the population normally distributed? If that's true, we're fine. So in fact, if either one of these has an answer of yes, if either one is yes, then the sampling distribution of the sample means is approximately normally distributed, and so we can use the central limit theorem. Right? For the individual value or mean of the sample, we need to determine whether we are using a normal distribution with a single value or the mean x bar from a sample of n values. Right? And so, are you working with an individual value, or are you actually working with the mean for a sample? That's where most students run into issue with this, is trying to weigh which one of those things they're working with. And think about that. So let's look at an example and see how this kind of comes into play. All right, so here we have our example. An elevator is rated for a capacity of 16 passengers with a total weight of 2,500 pounds. Weights of males are normally distributed with a mean of 182.9 pounds and a standard deviation of 40.8 pounds. So we're going to go through three different questions. The first is, what is the implied average weight of the 16 passengers if it is at its capacity? Right? So again, we saw above that the capacity of this, the weight capacity is 2,500. We have 16 passengers. So if it's at its capacity, then the implied average is that 2,500 divided by the 16. So the average weight of each of the individuals would be 156.25 pounds. All right, so that would be the implied average capacity, or implied average weight if it is at capacity. So then the second thing we want to look at is find the probability that one randomly selected male has a weight that is greater than 156.25 pounds. Right? And so what do we know about males from above? We know that their weights are normally distributed, have a mean of 182.9 and a standard deviation of 40.8. Right, so we know that weights for males are normally distributed. There is a mean of 182.9. And so we want to know what is the probability that one randomly selected male has a weight that is more than 156.25. Right? So somewhere down here to the left of 182.9 is 156.25. We want to know what is the probability that a randomly selected male has a weight that's greater than that. And we are looking at a single and individual male, right? And so we have here, we know for males, for individuals, their mean weight is 182.9. And we know that for individuals, their standard deviation is 40.8. So I'm going to go to StatDisk. And so over here in StatDisk, I'm going to choose Analysis, Probability Distributions, and then the Normal Distribution. We don't have an area. We have a z-value. And actually, I haven't calculated that z-value yet. So let me go back and calculate that z-value. Right, so let's convert this value right here, the 156.25, to a z-value. So 156.25 x minus the mean, so minus 182.9 divided by 40.8. That converts it to a z-score. So our z-score is 156.25 minus 182.9 divided by 40.8. And when we evaluate that, we get negative 0.653. Now that's not our answer, that's just the z-score, and that's what we're going to plug into StatDisk that we looked at on that previous page. And so we're going to plug in a z-value of negative 0.653, and I didn't get the negative there, negative 0.653, and let's go ahead and evaluate that. When we evaluate that, we have cumulative probability. So the probability to the left of that z-value is 0.25688, and the probability to the right is 0.74312. That's the probability we want, the 0.74312, because we shaded the area to the right. So let's go back. So our answer, our probability is 0.74312. That is the probability that a single randomly selected male would have a weight that is greater than 156.25. Now there we did not actually use the central limit theorem. So if you feel like we didn't use it, then you are right. It should feel just like things that we did in the previous sections. This next question, though, the next part, is find the probability that 16 randomly selected males have a mean weight that's greater than 156.25. And so now we're dealing with not individuals, but instead we are looking at a group of 16 different males in this setting, right? And so when we take a look at that, we're going to look here. Our mean of the means is equal to the mean of the individuals. It's still 182.9, but the standard deviation of the means is not the same as the original standard deviation. We actually have to divide that by the square root of the sample size. And so for us, the original standard deviation was 40.8, but we need to divide that by the square root of 16, which is our sample size from above. So that gives us 10.2 as a new standard deviation. So we're going to convert 156.25 we're going to convert that to a z-score. So 156.25 minus the mean, which is still 182.9, divided by the standard deviation, which is now, it's not the standard deviation of individuals, but now we're dealing with groups, a group, and the means, and how are the means distributed. So it is not the original standard deviation, but the original standard deviation divided by the square root of the sample size. And when we go through that, we end up getting a z-score of negative 2.613, approximately. Again, that's not the answer, that's just the z-score, and we're going to go back to StatDisk and plug in that z-score, find the area to the right of that z-score. That will give us the probability that we have a weight that is, a mean, an average weight that is more than 156.25. Right. So over here in StatDisk, again, I go to analysis, probability distributions, a normal distribution. and we're plugging in the z-score that we calculated on that previous page, which was negative 2.613. Right? And so we plug that in as the z-score, and we evaluate that. It gives us lots of information, but we want to know what is the probability, not from the left, but to the right, and that probability is 0.99551. So our probability to the right, 0.99551. And then this final question is really like just, what does this mean? How do we use this stuff? And this is how we use it, or this is what we need to think through it. Which probability is more meaningful when designing an elevator? Right? And so I want to think about, is an elevator used by an individual or is it used by a group? And an elevator is used by a group, so the average weight is going to have more impact on what's happening than an individual's weight. So that probability .9955 is more meaningful. And what that probability says is, whenever you have 16 randomly selected males get on this elevator, 99.55% of the time, their weight is going to exceed the capacity for that elevator. So most of the time, you're going to be over capacity. This was a real elevator. It was in a dorm room, a guy's dorm room at a college. And it's unsurprising that at one point in time, the elevator did go tumbling down, and there was a loss of life related to that. All right. Sorry to end it on such a somber note, but we'll look at another example in the next video.